Here I have another example. This one is an example of exponential decay. The example is using carbon-14, which is a radioactive isotope that decays in half over a period of 5,730 years, approximately. Okay, so the half-life of carbon-14 approximately 5730. So if you knew that a sample should, when it died, contain, say, 100 grams of carbon-14, then after 5,730 years, it would have half of that, 50 grams of carbon-14. The other 50 grams would have decayed and turned into another element. Okay, and so that's kind of how half-lives work. But there are some assumptions involved. You have to know what the starting point was, and without being there to measure that, if it's 10,000, 20,000 years ago, that's an assumption that we're making that may or may not be accurate. There are reasons why it probably is and reasons why it may not be, but anyway, you have to go with that, kind of trusting that information, okay? So we're going to go with it here. A petrified tree is found to have 15% of the carbon-14 that it had when it died. Again, assuming we know how much it had when it died. We express A as a function of T in years, okay? So our bodies are continually, this is for a human, this is for a plant, whatever, are continually ingesting and taking in carbon-14. When you die, that stops happening and the decay process begins. Well, it's always occurring, but the replenishment ends, and so the decay is more obvious and measurable. All right, so part A says express A. Remember, we have our exponential decay models as A of t. Express A as a function of t in years. Okay, so we know that in general A of t equals A sub 0 e to the kt. Because this is a decay model, we're assuming k to then be a negative number. And in this case, we know the original amount, we're just going to assume that to be 100% of the original amount, right? If here we have 15%. So we're just going to use these A's as percentages. We can do that. And just say that this is 100%. A sub 0 would be, we'll just go with 100%, okay? Which means that A of t, if I were to calculate this, A of 5730 would be 1/2 of that original amount, right? 1/2 of A sub 0, or in our case then 50%. Okay. Now when I plug this stuff in order to find the value for K, technically I don't need to know this 100%, I just need to know the half-life there. So we could use the fact that plugging in 5730 for T gives us that half-life. The half-life, 1/2 of A sub 0 is the output when you plug in the 5730. Okay, so by plugging in 5730, I get half of the initial value out. Now to solve this for K, I could start by dividing out the A sub 0. Now in our example, that would be equivalent to just dividing out 100, but it won't matter what that value is. We divide that out on both sides, and I'm going to be left with 1/2, go down here, 1/2 equals e to the 5730k power. To solve this, I'm going to convert it to natural log. So we're going to use the natural log of 1/2 is equal to 5730k. Remember, that's equivalent to just taking the natural log of both sides, and on the right, the natural log and the e will essentially cancel out using one of our commandments of logarithms there. And then to find k, I just divide the 5730 on both sides. So the k value is 1/5730 times the natural log of 1/2. Okay? And I can use my calculator to approximate that. the natural log of 0.5, close parenthesis, divided by 5730 is, oh, a very small number, negative 0.00012096.8. I'll leave it at that. There's a few extra decimals there, but we'll go with that many. My calculator actually put that in scientific notation, but I converted it as I wrote it down. Okay, so there's my decimal for K. So for part A then, to put all this together, I would say that A of t equals 100 times e to this times t power. So negative 0.000120968t power. Okay, there's our model. Now for question 2, part B here, it says approximately how many long has the tree? How long, not how many long, I can't even read. Approximately how long has the tree been dead? How many years, how long? I get them confused. Has the tree been dead? And so if we know that the final amount is 15% of that original, then we could plug the 15 in for the final amount and calculate t. All right, so we would say that 15 equals 100 times e to the minus 0.000120968t. And to solve that, I would again, I'd divide out the 100. Got to divide out the initial value first. Don't forget to do that. If you take the natural log right away, it's going to create an issue here with that 100. You don't want to just leave that hanging out. You can't really eliminate the e value until you've with a natural log until you've gotten rid of its coefficient. So we're going to divide out the 100. 15 over 100 is 0.15 equals e to our decimal times t. Now I can take the natural log of both sides and cancel the e with our property of logarithms. And so the natural log of 0.15 equals negative 0.000120968t. And to solve for t, I divide out by my decimal here. Okay, so I have t equal to the natural log of 0.15 over negative 0.000120968. And when I type that in to get my approximation, I'm going to go natural log 0.15 close parenthesis divide by the previous answer, which is about 15,683 years if I round that off to the nearest year. Okay, so 15,683 years later. All right, that's pretty close to 3 half-lives, right? Pretty close to 3, not quite 3 half-lives. Okay, so that answers our last question there. It would take about 15,683 years for that sample of C14 to reduce down to 15%.